marvelous thing to consider, really, and fantastic in its consequences for the human race. Consider the following. I have here a double track which is downhill to my left. Here I have a cylinder of wood which, as you know, will go downhill, as any respectable cylinder should do. But here I have another geometrical form, and I put it at the bottom of the plane, and lo and behold, it goes uphill. And that's a strange business. Well, friction forces are holding it there, so you see, it goes uphill. And a proper understanding of this lies in an understanding of center of gravity, an idea we got first from Archimedes in about the 3rd century BC. Consider a stick, a meter stick. If it was a good stick, as I would like to have it, it would have to be uniform, homogeneous, and isotropic. Those are wonderful words to know the meanings of. Supposing the stick weighs 10 pounds, and I support it with 2 fingers like that. It is clear that each finger pushes up with 5 pounds each. 5 plus 5 is 10. The stick weighs 10 down. Indeed, if I move the fingers elsewhere, I still exert 10 pounds up, but in 2 places. Now, can I not find a place such as that right there, where I exert a force of 10 pounds up? And we are then led to say that all the stick is right there, all of it. And that's the center of gravity of the stick. Incidentally, I could use also the phrase center of mass, and I leave it as an exercise for you and your teachers to find the difference in center of mass and center of gravity. Now, I said all the stick is here. This suggests that there's no stick here and no stick here. And somebody says, but I see some stick here. And I say, all the stick is right there. And I could prove it. Let me put a clamp on the stick and support it somewhere remote from the center of gravity. If I do that, the stick tips. Obviously, anybody knows that. But if now I put another clamp on the other side and find an appropriate weight here, you will see an astonishing thing, that I can put the stick in equilibrium. On the ground that all the weight is at the 50 mark. So, on the blackboard, it would look like this. Here is the stick. There is the center of gravity in the geometric center, and I have supported it right here with a weight hanging here. And I say that if we consider all the weight of the stick, W sub S, acting right there, then that weight of the stick times that distance there is equal to this weight times this distance here. And so we can find the weight of the stick without weighing it by assuming all the stick is right there. Now, to prove that you are right when your teacher does this, all you need to do, having done the mathematics, is to put the stick on a platform balance in such a fashion and weigh it. And an astonishing thing is discovered. A very astonishing thing. That the weight of the stick is exactly what you get, disregarding some little experimental error, exactly what you get by assuming all the stick there. Let's consider it further. Here is an equilateral triangle. If I put a pin through one vertex or corner and hang a plumb line on there, a plumb line is just a string with a bob on the end of it, and such a plumb line is always vertical for the observer at the place in question, and then I draw a line on that triangle, I say that the center of gravity lies somewhere on that line. Proof. Let me do this from another corner, such as, say, this one, which isn't broken. And we see that the plumb lines intersect at a place. This place is the center of gravity of this triangle. All the triangle is right there. Proof. I am going to put my finger right there, and the triangle will remain in a horizontal plane, which was announced by Archimedes, again, in the 3rd century BC, in a classical book which he wrote entitled De aqui ponderantibus. See, concerning equal ponderousness. You can discuss this with your classmates and your teacher. So the center of gravity of this equilateral triangle, for those of you who know a little geometry, is at the intersection of the medians, at the intersection of the angle bisectors, at the intersection of the altitudes upon the sides, reviewing a little bit of Euclidean geometry. Consider another triangle, an isosceles triangle, the center of gravity found in the same way. Or consider an irregular body, center of gravity found in the same way, the intersection of the plumb lines. Of course, the center of gravity of a uniform circular plate would obviously be in the very center. Now, in all of these illustrations, we have found the center of gravity to be where? Where there is some stuff. There's some stuff there. So the question has very intriguing complexion, because here, if I hang this up and drop a plumb line, it goes so. If I now drop another plumb line, it goes so, and we see a most remarkable thing. Very remarkable. The plumb lines intersect where there is no stuff, right in here. And this is the center of gravity of this slab. Moreover, all the slab, all the plate, may be considered to be right here where there is none, which is a most astonishing piece of business. So the center of gravity of a system can be where there is no stuff of the system. This leads me to ask, where is the center of gravity of a donut? The center of gravity of a donut is in the middle of the hole. And if you cut out the middle of the hole, or cut out the hole, I have in my right hand the center of gravity of this donut, which is a very remarkable idea. Now, to show you the consequences of this, let's look at this rolling down business. The uniform cylinder rolls downhill. Its center of gravity is in the geometric center, along the long axis and in the middle. If we measure the height of the center of gravity above the tabletop, which I would call the zero potential plane, measure it there, then measure it down here, we would find that this is lower than this. Accordingly, the center of gravity has gone downhill, which introduces another very fundamental principle, namely, that the energy of a system tends toward less. So this goes downhill. The center of gravity has gravitated downhill. On this one, the center of gravity of this double cone, referred to as a cone of two nappes, N-A-P-P-E-S, beautiful geometry established by René Descartes, the Frenchman. The center of gravity of this double cone lies along this central axis and in the middle of this single base. So when I put the cone here, the center of gravity is so high above the zero potential plane, the tabletop, and where is it now? It is clearly nearer the tabletop. So again, the center of gravity has gone downhill, although it looks as if this is a crazy piece of business, that the cone, stuck a little by friction there, the cone appears to roll uphill. So the center of gravity, very important idea. More of an astonishing nature. Here is a cork stopper. Here is a cork stopper with a pin in it, and there's the head of the pin. Here is another cork stopper with a pin in it, and that's the point of the pin. And if I put these point to head in this position, if I can find that position here, and let go, obviously it will not stay stably. It will tip over. Why? Because the center of gravity is above the point of support, a condition that is not good for equilibrium. So what do? I put a couple forks in here, in any way whatsoever, and then I put the point of the pin on the head of the pin, and there it is. Let me get this away so it doesn't hit the glass vessel, and we see an astonishing thing. Just look at that. Should not that fall off? It should. But why doesn't it? It does not fall off for this reason. The center of gravity of this system is below the point of support, which is another condition of equilibrium. Here's a good illustration of it. Take this little man, a little metal figure in the shape of a man who supports himself, you see, on the toe of one foot. And that's fantastic, really. He is very stable. If I tried to knock him off, oh, that just slipped there. That didn't really fall off because of the inadequacy of the center of gravity. Look at that. What must we say? We must say this, that the center of gravity of this man and his rod and the sphere system is below the point of support, which makes him stable. I say the idea of center of gravity is an astonishing one, as I remarked earlier, in its consequences for the human race. Consider this one, more of the same. And I hope you see that I am injecting into this program some elements of fun and jest, because, as I like to say, the intellectual process is usually very severe, so it needs some fun injected into it to make it a little more palatable. Here is a figure most stable for the same reason, the center of gravity below the point of support. Of now fundamental interest to us is such a program as I have here. Consider this block of wood. Square cross-section, cut askew on the bottom. It is so stable. I call your attention to a plumb line that is supposed to be inside at the center of gravity, and that plumb line falls inside the base. Now, let me put another block atop the original. I hope you see what has happened. I have raised the center of gravity and shifted the plumb line to your left, my right, so that the plumb line passes more nearly on the inner edge of the base. The system is now less stable. If now I put another block atop, it is obvious what the consequences are likely to be. The center of gravity has been raised, the plumb line is shifted further to my right, and may indeed fall outside the base. This makes the system unstable, as you will now see. Notice, the slightest displacement is likely to tip it over. So, if a system is stable, as we say in physics, what we mean is this. Any slight displacement from its position of equilibrium will still allow it to return to where it was. If it is unstable, as we have now, because the plumb line falls outside the base, any slight displacement will raise havoc with us. Watch it. And it tips over. You know what I am representing here. I am representing the Tower of Pisa, which I hope you know about historically, and I thought you would like to see a picture of it. In Pisa, in Italy, and I hope one day you will go there to see it for yourself. I say it is a most wonderful thing to contemplate. So, ladies and gentlemen, and boys and girls, we come to the end of our first lesson, let us say, on the great idea of center of gravity, the notion first established by Archimedes. And I thank you for listening.